My name is Meena Mahajan. I am a professor in the Theoretical Computer Science group at the Institute of Mathematical Sciences, also known as IMSC or Mat Science. And today we are presenting the 7th edition of this annual event, Science at the Sabha. The previous 6 editions took place at the Music Academy. Many of you, I think, were there at those events as well, and I'm happy to see you here again. Those who are coming here for the first time, fresh welcome. This is the first time we are experimenting with this venue, the library, repository of knowledge. It should spur us on to learn and to discover more. In this annual event, we bring to you exciting talks about current topics in scientific research. Research that is taking place in India, around us, mostly in publicly funded institutes and universities. So today we have 4 such talks for you. Before we begin the first talk, can I request everybody to make sure that your mobile phones are on silent mode. Can you show the slide about that? Okay. So I'm not saying switch off your phones. I'm saying keep it on silent mode because you will need your phones to be on if you want to send in questions and comments for the speakers. At the end of each talk, we will have a very short question and answer session. Questions which have been sent in on by SMS or on Facebook or on X, formerly Twitter. You should have got the coordinates in your registration email. We will also try and show the slide again at the end of the talk. So these questions will be collected here and I will put them to the speaker on your behalf. At the end of all the 4 talks in this event, we will have another question and answer session where you can send in questions for all the speakers. Okay? So with that said, we are ready to begin our first talk. Our first speaker for today is Annapurni Subramaniam. She is an optical astronomer. She works at the Indian Institute of Astrophysics in Bangalore. This is where she did her PhD several years ago, and today she's the director of this institute. Her research interests include star clusters, young stellar objects, straggling stars, nearby galaxies. She's a calibration scientist with the Ultraviolet Imaging Telescope, which is on board India's first astronomical observatory. Her group has worked on developing software for the international consortium, which is building the 30-meter telescope. And she is also a member of the International Astronomical Union, which is the leading authority for giving official names and designations to astronomical objects. She's a fellow of the Indian Academy of Sciences. She's a fellow of the National Academy of Sciences. And today she is here to tell us more about astronomy from the ground and from space. Over to you.
The Indian Institute of Astrophysics has its origins in right here, Chennai. Because when it started, I'll be talking about it. It started as a Madras Observatory in Nungambakkam. And then it moved to Kodaikanal in 1899. So it worked here from 1792 to 1899. So there you go. So I have my first slide. So I'm here to talk to you about my passion and also how we have been doing, how I have been doing, and also people, before me, how we do astronomy. And astronomy is something which you observe the sky and which we have been doing from very ancient times because astronomy is one of the older sciences. So how we have been doing that and how we do now, and we all know that the yesterday's launch, the GSLV launch yesterday evening. So we know that we have huge space capability as well. So we do astronomy from ground and space together, right? So that's the era. And the background image which is shown here is Stephan's quintet. It's basically a set of interacting galaxies. Now, why do we do such a grand scale, instrumentation, very complex engineering? Because astronomy is an engineering-driven science. So what do we actually achieve? So this is basically so you can see that the most complex instrument up in space is the James Webb Space Telescope. I'll be talking a few points about it. But it's giving us the fantastic pictures of the sky in a particular wavelength range, right, in the infrared. Now, if you take it and give it a color, because infrared eyes cannot see it. So if I'm telling you that if I'm detecting an infrared image, how do I convey to you what I have detected? I have to show it to you in an image or in a wavelength where it is your eye can see it. So in astronomy, one thing, bottom line, is that all images, most of them are false color images. Many of them are false color images. But what is then true about the image is the intensity. Intensity is true, but the color may not be true. If it is invisible, we'll give the right color. But if in the infrared and I have to show you what it looks like, it's a false color. Similarly, so this is the infrared, but it's in yellow. It's represented in yellow. But JWST does not see in ultraviolet. So what does this galaxy do in the ultraviolet? Why ultraviolet? Because certain physical processes emit the wavelength in ultraviolet. Now, we have taken this image from UV imaging telescope. It's a Indian, part of the Indian space mission called AstroSat. So that picture of the same, the picture from UVIT, it's ultraviolet. So I cannot show an ultraviolet image, right, because I cannot see it. So I will give it a blue color. So what intensity I got in that image from where, which location? So that is depicted in blue here. You can see that it is different. You can see that image of 7318 A and B, it's like a smiley, right? So the galaxies are sitting at the center, which has got the JWST saying this is where the intensity is, light is coming from. But any ultraviolet light, no, it's coming from elsewhere. So this basically depicts the importance of precise measurements and also multi-wavelength, because if you did not have the ultraviolet image, then the physical processes which you would give it to this particular object will be completely different. Now you have ignored the entire thing which is happening around it, right? So now you'll ask what physics? I'm not going to talk about it, that's for another talk. But this image is to tell you that it is important to have multi-wavelength coverage, because an object like a galaxy or an interacting galaxy will have multitude of processes going on. So to understand the full physics, what's going on out there, you need the multi-wavelength data. So this is a combination of Indian observation as well as the observation from JWST. It's one of our students, Joseph, did it. Now going to the next ones, basically the astronomy started off with ground-based observations since Galileo pointed the telescope up to the sky. Now, when I was a student, I used to go to an observatory to collect data and do it. Now, the data democratization, you can actually see the websites and download the data and what you can do, whatever you can do with it. But olden days, like 30 years ago, you did not know where data can be obtained. So you have to go to an observatory. So I spent my time at the Vainabapu Observatory when I was a student. This is also in Tamil Nadu, very close to Vellore. This is in Javad Hills, okay? So you can see the domes, two domes. One is a 1 meter telescope, and the other is a 2.3 meter telescope. So a lot of such telescopes are located in a kind of remotely located places where you have a decent night sky and free of clouds, mostly free of clouds, and also light pollution. So you can't have it in the city. Now, I do not know how many of you actually have seen starry nights. I used to see it when I was a kid, thanks to something called power cut, right? So you couldn't do anything. You have to go out because inside it's very hot. You go out and then start looking at the sky and start wondering what is it, why is the patterns, and it starts a lot of curiosity questions and you start chasing them. Of course, there's no internet there. You can't Google it out. You have to go and talk to people or go to a library and take a book and read. So getting information was so difficult then. So the ground-based telescopes have been the workhorses of astronomical research, and India has contributed to it as well. Now, you can also, this is our observatory in Ladakh, which was established in the 2000s. And this is on the right side is a 2 meter telescope. This one is the Himalayan Chandra telescope. And these are the gamma ray Cherenkov radiation detection instruments, MACE and Hagar. Now, this is a wonderful picture taken from Hanle of one of the meteor showers. So this Gemini's meteor shower, image credit our engineer in charge, Doje. Maybe many of you are followers of him in Insta as well. He produces wonderful pictures. You can see the meteor shower starting from the Gemini. You can see the Gemini stars This is not one shot, it's like taken over the entire night and combined together, but it actually gives the feel of what it is like. And similarly, this is our galaxy. So you can see lots of stars and the dark lanes, the patches, and the dust lanes in this. The most important thing is these, though they are small telescopes, so 2-meter class, but ideal locations like this produce wonderful science. We also have telescopes like this, this is the 2.3-meter Vainu telescope. This is indigenously made in Kavalur. And this is the 3.6-meter, one of the largest telescopes in the country right now in Nainital. So this is in Devasthal. But you can have, these beasts up in the sky. These are very big systems. Can you lift them up? Issues. Because if you forget a bolt to put in, you can always go and step out and fix the bolt. Now that doesn't happen in your space payloads. You have to make sure that everything is in place, everything is screwed up the way you want, not more, not less. If it is less, it starts rattling. If it is more, it can break. The tension is too much that it can break. So you have to figure out what angle you have to torque it. So extreme care is required. And also that your planning stage itself, each joint, each wire which you are fixing has to survive the space. If you're forgetting to take care, it can fail. So the risks are too high. And the amount of effort required to lift up the huge thing and put it up there is also quite expensive. So there are trade-offs between the ground-based system and the space-based systems. But then the goal is to get a sharper view and a multi-wavelength coverage, because the Earth doesn't allow all the wavelengths to come in. And that, of course, is the reason why the life is also persisting, right? Because it is stopping the high-energy rays from coming in. But that does not mean that the objects out there are not emitting high-energy rays. So if you want to catch them, you have to put your instrument outside the atmosphere. So that's an important requirement. Cognizant of that, the Great Observatories program, basically it's a joint effort by the NASA and the ESA, the European and the American space agencies put together these observatories. So you can have the gamma ray one, the X-ray one, the optical, and the infrared. Now you know more about the HST, less about the others, but these are the part of the Great Observatories program. But we also have an observatory which is a multi-wavelength, which is AstroSat, launched in 2015. So many of them actually, you plan it for 5 years or 10 years. Sometimes they last more, sometimes they last less. But if you look at the HST, it has completed more than 30 years. Now, the AstroSat launched in 2015. We had a 5-year lifetime, but now it's more than 8 years. It's still working. So I was working on this is the UV imaging telescope. The first image where you saw the ultraviolet, it is coming from this particular small, actually it's a relatively small telescope. Now what do we do with this? Basically it helps you to get fainter objects. You can have fainter and fainter objects, which could be distant. So you're actually looking far out into the space as well as looking into the past. So you can actually see how the universe is formed and what things are out there, etc. So these are the kind of things which you see. And the James Webb Telescope has already actually seen up to about 500 million years since the beginning, right? So Hubble Deep Field actually is one of the observations where it gave a lot of information. The James Webb Space Telescope is another engineering marvel up in the space. This is the first multi-mirror instrument. So if you look at Hubble has got how many mirrors? The primary mirror is single one, right? Single mirror. But do you know how many JWST has got? I'll give you an example. It's a 6.5 meter, okay? So you have a choice of flying of 6.5 meter up in space. It's very difficult. Make sure that it doesn't break, nothing happens, fly up there and put it up there. The idea was actually not that. You actually can make it to smaller segments and put it up there. The question I want to put forward is, it's an engineering problem. You have small telescopes, which are lenses basically, right? You have one lens and you look through it, the light comes and the focus comes here. Now, how big can you make the lens? Can't be bigger than small, little bit. What happens when you make bigger lenses? It becomes too heavy. It's too much of glass. Too much of aberration. So do you want lens? No, you go to mirrors. So you have mirrors and then bring it to the focus. You can put the instruments, etc. Now, how big can the mirror be? As I mentioned, it can be 1 meter, it can be 2 meter, it can be 4 meter. Now we have 8 meter also single mirrors. What about 10? Does it stop you from making bigger telescopes because the technology doesn't allow you to make bigger mirrors? No. What do? So the entire approach changes and you go to a multi-mirror. So that is, but basically you're telling yourself that you make small segments and not about polishing, each has to be polished and also each segments have to work as a single, the entire thing has to work as a single beam. Basically you have to polish it properly, you have to hold it properly. It's not just sitting idle, it is turning because if the object is there, the telescope has to turn, right? So you have to have a lot of computer engineering support system which has to work together in sync. So it's hugely difficult. In fact, this is the payload where each mirrors, please go and look up how many mirrors are up in the JWST. So this is a multi-mirror, first one up in space. And not only that, it's working infrared because all these are stopping the heat. And I'll tell you where it is located because it is also equally important where you want to place this beast. Can you place it anywhere you want, any kind of orbit you want? That also one has to choose. And depending upon where it is going, the power requirements, electronic requirements also change. Now, what is it about? So, what kind of orbits it goes to? So, first is the LEO, which is the low Earth orbit, which actually about 300 to 650 kilometer. The most important things, very familiar ones, are the International Space Station. It's about 300 kilometers. The HST is at about 650 kilometers. It goes around the specific place once in 90 minutes. If you take example of AstroSat, it's got a 650 kilometer orbit. Every once in 90 minutes, it goes over Bangalore. So that you can upload your comments and download your data. You can also have, you should remember that when it does, it is an equatorial orbit, where the Earth is there, the sun is there, it goes like this. It sees the sun sometime, then it goes behind the shadow, then it can see the night sky. So where you want to look at, it will be like 50-50, right? You're looking at sun for some time and then the dark sky for some time. But if you don't want to do that, you want to have both together, then you can have a polar orbit. The other one, that's the middle one. There's also another orbit where you can have geosynchronous orbit, right? That's where the yesterday's INSAT 3DS has been launched to and placed at. That I'm not putting here. But there's something else where astronomers are very interested in. Apart from these two, that is the Lagrange points. You might have heard that the Aditya L1 mission is gone to the Lagrange point L1, yes. So L1. Now, what are Lagrange points? This is basically a two-body system. In the two-body system, you may have some points where the gravity kind of balances. So it depends on how big these objects are. So the point which balances between the Earth and the Sun will be closer to the Earth, right? That's very intuitively, you can draw a straight line between these two bodies, and the point in between will be where it is balanced. It can't be midpoint because the bodies are of not same mass, so it will be closer to the Earth. But there's also, mathematically, you can actually find a point on the other side, which is called the L2, right? So this is the L1. So I'm showing the Earth Sun system Lagrange points. This is the L1. So it is between the Sun and the Earth. You will also have L2, which is behind the Earth, 1.5 million kilometers. Now, here if you have the Webb telescope is in L2. Why L2? Because you will be always in the shadow region. So you can always have the night sky. But how are you going to get the power? The panels have to see the sun. So they go around the orbit, large orbit, so that you look at the night sky, but the solar panels which is on this side sees the sun. So these are the requirements. Now if you look at the Aditya mission, what it has to do, it has to look at the sun all the time. So if you put it in the LEO orbit, half the time it is looking at the sun, half the time it is behind the Earth. So you won't get 24-hour coverage. So you have to take it out of this no shadow region. If you put it at L1, you will have a continuous coverage of the sun without any blocking. But it's 1.5 million kilometers towards the sun. We have not done it before. This is the first time we have done it, and the spacecraft has reached there a month ago. And you also remember, you also should see that there's no object at L1. It's a fictitious place. So you have to figure out the orbit by yourself because there's nothing to focus on, right? So the distance has to be not with respect to L1, but something else. You have to figure it out. So it's a different problem altogether. And also, Earth is not stationary. It's going around the sun. So L1 will also move. So imagine what happens in 1 year when Earth completes one rotation. The L1 also will make an inner rotation around. So the instruments on board this mission will also measure the kind of particles on the inner circle as well as the magnetic field. So you'll have a large amount of data which is inside to the Sun-Earth system. So that is one of the unique things which the Aditya L1 will be doing. Now, you have all this data. To do science, the raw data is not of much of importance. What is important is otherwise everybody will have to look at the screw and driver, and you have to how to actually curate the data and get it so that you can do the science. A lot of processing happens between the raw data and the science study data. Now, as a student, I used to take each and every frame, make sure that all the corrections are done, and finally, it takes a lot of time to create the science study data so that you can do science. But when the volume becomes very large, you can't do these manually. You have to do a lot of pipeline, and then the pipeline should deliver science study data so that the students or the researchers can start doing it. Now, not only pipelines, the data which is produced also has to be disseminated. That means archives, where you can go and find out. I have an object, interesting object. Now, how do I know how many telescopes have seen that particular object and what data has it produced? If there's an archive, ready to use data is already available there, then the science can be done very easily. Otherwise, you will say, like cooking a dish in the kitchen, you have to think of all the ingredients, you start planning, and then you go and buy everything and buy and make the dish. You have to start 1 week ago, right? So it takes a lot of time. The productivity and the science and the output gets reduced. So ready to go cooking data has to be there, archives have to be there. So we are also improving, and these are the data which is available from, the NASA has all this up in the MAST archive or HISAC archive. Not only that, they provide software, also places where they can keep the space for downloading the data because the data volumes are becoming large. So all these verticals have to be ready. If you have a mission going up, the data coming down, and the science and the publications and the research outputs coming up. So without these verticals, things will not happen. So it's happening, and it's very nice. Now you can all ask, okay, it's very interesting that astronomy is very nice, it's very exciting, but what is the use? Why should you do it? 2 points. One, astronomy started off with 2 objectives for humankind. One is navigation. Olden days, you don't know which way to go, so it gives you directions, And second is time. Now, morning, evening, etc. But what is its use now? Do we still need astronomy for these? The direction, time, of course, you have atomic clocks which gives you precision, but still we look at seasons and morning and evening with respect to sun and moon, etc. Right? But what about navigation? You don't look up now, you look down. Where? To your mobile for maps. Now, how does that work with respect to positioning systems, global positioning systems, GPS, right? But GPS, how does GPS work? GPS is also a set of moving satellites. It needs reference. So absolute reference still comes from astronomical objects. So you need actually each and every object's position, its motion with respect to year by year. The positions happen, we have to accurately do it. And over and above everything, one more point comes from physics. The GTR. So you have to correct for the general theory of relativity. The relativistic corrections have to be applied for precision. So all these go in order to get accurate positions. Anything else? Yes, of course. We have celebrated 150 years of periodic table a few years ago, 155 years. Now, where did all these elements come from? Who's cooking it? Definitely not. We are not cooking the elements. Who cooked the elements? How did we come into existence? Now, we know that this is a periodic table where it lists out which elements are formed from which type of stars. Stars are nuclear reactors. They have the temperature, they have the density, and the neutrons to make different types of elements. That's where the elements are being cooked. Now, before the solar system formed, the certain stars existed. They made these elements. When they died, they threw out these elements, polluted the system. And that's where it started off with. So, astronomy gives you chemistry, and it also how exactly these elements are formed, etc. And you also see a large variety of temperatures where different types of reactions can take place, starting from making ions, making molecules, etc., etc. Now, how do they throw up? This is exactly the reason. Like the sun we know is converting hydrogen to helium. Don't take my word for it. How do you know that? It's proved because we do see an output of that, the neutrinos. So we do detect it, right? So sun-like stars cannot make many more elements, but large massive stars can produce up to iron. And when it collapses, the remnant either becomes a neutron star or a black hole. Then the entire outer layers, it's actually, we call it as a supernova explosion, but it's an implosion. Implodes and the outer layers expand, and all this ejecta will have all these elements. You also can make higher elements by neutron capture. So there are several types of reactions go in. So that's why we said that we are our isotopes, and this is how the solar system composition come up. I just want to, so this is the brief history I was talking to you about in the beginning. So this is an observatory set up in Chennai, Nungambakkam, and then it moved to Kodaikanal. And it became an autonomous body in 1971 called the Indian Institute of Astrophysics. We moved its headquarters to Bangalore in 1975, and we completed 50 years in 2020. It's under the Department of Science and Technology. Now, we started off as a small observatory. Now, what do we have? As I mentioned, we have 2 centers in Bangalore. One is the urban center, the other is the rural one, where we actually integrate our space payloads. And we have one radio observatory in Gauribidanur. Kodaikanal is our solar observatory. Kavalur is our stellar nighttime observations. And we have 3 centers in Ladakh, Hanle, Merak, and Leh. And we are setting up a planetarium in Mysore, which is actually, in planetarium you have an inert dome, and you project the whatever movie or the sky pictures through a projector. But what is it happening here now on the screen? Is it a projector there? No, it's an LED screen. So the planetarium in Mysore will have an LED dome. There won't be any projector, but you will have an LED dome. So this is the first of its kind in the country, and do come over and visit when it opens up for operations and public viewing by end of this year, hopefully. And we have the Astrosat, the UVIT on Astrosat. We also have we also made the chronograph on the Aditya, and we're also party to the 30-meter telescope project, where we host the coordination center. So these are some of the pictures of various centers. You're welcome to visit. Just a few words on Aditya L1 mission. So this is the mission, and this is a picture of the sun when you actually block the center of the sun. So the central, this particular disk is the actually size of the disk. Now this is blocked a little more than the disk, and you can see the coronal mass ejections coming. So this is the one which hits the Earth or the space weather and large particles up in the space, etc. Right? Now the idea is the coronagraph. This is a coronagraph image. Coronagraph would mean that you are looking at the corona of the sun. Normally you see the corona during only the total solar eclipse, because the corona is too faint to see it. You have to block the disk. Just like, do you see the stars in the daytime? No, because the sun is too bright. Similarly, the sun is too bright that its corona can't be seen. So you have to block the sun. So can you do it all the time? Yes, it is possible if you can block the sunlight within an instrument. It's very difficult. It's a complicated job, but you can do it. So that's a coronagraph, and that's what is up in the space. But the idea of this instrument is that you can look as close to this disk, because you know to trace where exactly this is being launched. Because now you cannot connect this with where it is coming from on the sun. So the idea is to connect it. Now, we do have a heritage. This 1899, we started this Kodaikanal observations, and we have observing the sun continuously since 1904. Now, why do you do this? Because you know the sun is active, and the activity cycles is of the order of 11 years or so, and there is a periodicity, and the activity goes down, and all cycles are not the same. What to expect the cycle? How do I know? Can I model it? Lot of data is required. So this actually helps, and we have digitized all this data and calibrated, and it's up for anybody to look at it and do science with it. So now that we've been doing for more than 100 years, what else do you want to know? It's not clear because the magnetic activity is not predictable. We're still trying to predict it, whether we can predict the next cycle. And second thing is many dynamic events happen. We didn't care much about it in the past, but with our space asset increasing, these particles can damage our space asset. So it's important for, all the more important to understand space weather. Now, how do we see the corona? Corona is very hot, 1,000,000 degrees. Now, can you detect it? The temperature is so high. What happens if you heat a gas? It gets ionized, right? It start losing some ions. So heat up a little bit, you can see the recombination and it falling down. But it's 1,000,000 degree, what will you expect to see? In most cases, the elements will be completely ionized. You won't see any recombination. What we are going to see is the ion recombination of some lines such as 14 and 18, etc. So here looking at, iron 14, iron 11, iron 12, etc. This is one of the very rare places where you are looking at, ionization of iron up to 12 electrons outside is taken away. So that temperature does it, and you have to have help of atomic physics, etc., to figure out that energy transition, how it happens, and how you actually are you getting it right. Okay? So this is the kind of science we'll be doing it. And this is the spectrograph, this is the coronagraph, and this is the spectrograph where we'll be taking the spectra in these lines to find out how much is the ionization, how many electrons are present there, electron density, and also the way in which it is progressing, because you also get the velocities, like the Doppler shift. If you know the rest velocity, so you can actually rest wavelength, you can also actually measure the shift, so it will tell you how much velocity the wind is moving, right? This is a complex instrument, so this is the kind of optics you have. And remember, these are all put it in a place and make sure that it is not, it should not move at all. So we have to make sure that it is perfectly placed and intact, and none of the optical elements break, none of the fixtures break, and function properly in space. These are some of the pictures, and this is a high contamination-free area. We have a clean room facility. That's where it is made. And a few things about the 30-meter telescope project. As I mentioned, when you go from 1 meter to 30 meter, we change from single mirror to multiple mirrors. Now, this has got 492 segments. So it's like a football field. So it's huge. And every segment is about 1.4 meters aperture. And it's not circular. You have to cut it. So you have to have technology to have a roundel, polish it, hex cut it, and have shapes. Design, the entire thing has to be designed and done. So we are actually commissioning a laboratory in one of the campuses where 80 such mirrors will be fabricated. We are starting it, and probably in a month's time, we'll be qualifying the first mirror. We also are producing, with the help of industry, all the support systems. Not only the mirrors, you have to support them, right? So these are the support systems, and these are the segments sitting on it. And we also know how close they've got, because you have to align them. It's a nanometer scale. So all these are Indian industries are doing. We're partnering with about 70 qualified, and then about 20, 25 are actually delivering the instruments. So these are in-kind deliveries to the project. These are some of these pictures. So this is like the mirror polishing thing, because it's like a stress mirror polishing thing. So this is a highly complex stuff. So what's future? We are looking at a more ground-based telescopes, like the large solar telescope. We have already acquired the site, and this is the bank of the Pangong Tso Lake in Ladakh, because if you look at the sun, it can cause a lot of turbulence. So you need a kind of breeze to take the turbulence, the heat away, so that it cools down. So this is the site, and we also have plans for the large optical telescope. and another space mission. Now, since this talk is titled the Sabha, so Science of the Sabha, I'm also a musician. My parents are musicians, and they are both my parents are vocalists. My mother is no more, but my dad, who's 88 years old, still sings. Every day he sings and tells me that today you have not played violin. I'm a violinist. I accompany my father on concerts, and I hope I can play this audio.
So the questions have come in on X as well as by SMS. There's one question from somebody whose name I do not know, phone number ending in 5736. It asks, if the goal of placing telescopes in the Lagrange points is to use gravity rather than fuel and to keep the telescope in place, and you need to shield the telescopes from the sun, then won't the telescopes keep getting pushed away by the energy of the sun?
So basically, the sun's energy is not what is pushing it there actually. So you have to keep it in. There is a gravitational because it's the line it is balanced. So you don't have much thing to, if you create you have a vertical plane where you actually place the orbit. There is very little energy required to push it there. So the gravity will take it. It's not really stable, but then energy required to put it in the orbit is very less. So that is why it is preferred. It's not pushing. Yeah.
Okay. Thank you. This is a question from, I don't know the number also, the person who has sent it. What is the reference point for the space-based telescopes? How do you position the spacecraft for precise observations while orbiting the Earth? You briefly touched upon this point in your talk.
There's something called star sensors, because you need to have star sensors in place, because you need to know the array deck or whatever coordinate system you are looking at, right? So how does the intelligence on board know which is the direction? So you need to have a lot of coordinate system, like the spacecraft itself will have a role, your coordinate system, but you have to also draw your pitch, but then that has to be marked with your array deck, which is basically the coordinate system you see in the sky. And then someone has to say which is the axis of this telescope is oriented with respect to the sky. Now that you have to do even for the ground telescopes. Because if I put a telescope here and if I put a telescope in Delhi or Ladakh or somewhere in Korea, Japan or somewhere, things have to be coordinated. So you think the sky is not the same. So you have to coordinate that. But star sensors which look at the sky and take a map and compare, it will tell you which direction it is pointing. So first of all, that comes in place. Look at the sky, coordinate, and then you have to orient with respect to that, the telescope to the object. So generally you get very good pointing.
Sanjay, in the context of astrophysics and orbits, could you explain perhaps the main principle and what could be the biggest value output of Elon Musk's Starlink project?
It's a very complex question. There are too many things in that question.
I agree. Would you like to address any of them?
It is good for a good 1 hour talk.
Okay. So we take this offline and okay. One more. There are more questions which we could come back to later. One very short question from a person with phone number ending in 8470. Can you comment on this whether Pluto is really a planet or not?
Okay. So that's see, when I was a student, of course, Pluto was a planet because that's the only solar system we knew, right? So everything what you could see, put it as a planet and go ahead with it. But the problem started when you started looking at similar systems outside. Then you started looking at, okay, can that be a planet or not? What is this a planet? So too many questions, ifs and buts came. So if you have to look at, it's like your own house, you constructed, everything is fine. This is the way it is. But now similar houses came, then you said, is it a big house or a small house? How do you categorize it? So when you start to put categorizing, you have to have certain principles. When you apply the principle to someone else and not apply to you, then you are in trouble. So if you want to streamline that, that is how, so with certain criteria, Pluto went out of the system. This in very simple terms.
Thank you very much.
Thank you.
So join me again in thanking Annapurni for this very interesting talk.